Hello dear students, welcome to a new session. In this session, we'll be starting with the first chapter of organic chemistry, which is haloalkanes and haloarenes. Now this organic chemistry, it is basically a branch of science which deals with carbon and its compound. Now since we will be discussing about carbon and your organic chemistry is filled with carbon, we have to remember tetravalency of carbon. Now just as every element needs to fulfill octet configuration in order to become stable, in the same way carbon also has its own rule. Now let us see what rule carbon follows. You can see here tetravalency. The configuration of carbon, we have carbon 6. So here 1s2, 2s2, 2p2. So the valence shell consists of 4 electrons. Now for carbon to become stable, it needs to have 4 more electrons to acquire octet configuration. Now carbon, if it accepts 4 electrons, that means it will become anion. So 4 plus 4 will become 8 electrons. But you can see here, carbon is designed to have only 6 electrons. If 4 more electron is added, altogether it is going to have 10 electrons. So for the nucleus of carbon to hold 10 electrons together, it is not possible. That is why accepting of 4 electrons is not possible in case of carbon. Now let us see what happens if carbon gives away 4 electrons. If carbon gives away its 4 electron, it will be left with 2 electrons. But to give 4 electrons or to share 4 electrons, it needs huge amount of energy, which carbon does not possess. If it gives away 4 electrons, it will become cation. But carbon do not have that much energy to give away 4 electrons. So this is also not possible in case of carbon. Now how will carbon attain stability? Carbon has only one possibility, that is to form covalent bond. Now what carbon will do is, it will share its electron. It will not give away nor accept, but it will form covalent bond. Now since it has 4 electrons in its outermost shell, carbon always form 4 bonds. Now this can be anything. It can be hydrogen, it can be chlorine, it can be anything. But the rule for carbon is that it needs to have 4 bonds. And this is known as the tetravalency of carbon. Tetra means 4. Now whenever you are writing any carbon compound, the first thing you have to keep in mind is its tetravalency. Now here, if we have C2H6 and we are to write this in the format C. Now we have to keep in mind that carbon has to fulfill its tetravalency, otherwise that very compound will not be stable. Now we already have one bond. This bond will be shared by this carbon as well as this carbon. So it already has one bond. Both this carbon need 3 bonds now. This carbon already has one, so it will be written in this manner. This carbon also needs 3 bonds. Now hydrogen, never leave this space empty. If you leave this space empty, it will be considered as methyl group. So always write down the substituent. So here, carbon, carbon. Now you count the bonds. This carbon, how many bonds? 1, 2, 3, 4. Tetravalency fulfilled. Now this carbon, 1, 2, 3, 4. Tetravalency fulfilled. Now suppose you have a double bond. This carbon already have 2 bonds. This carbon also has 2 bonds. Now each of this carbon needs 2 bonds to become stable or to acquire tetravalency. Now let us see for this carbon. Carbon 1, 2, 3, 4. For this carbon 1, 2, 3, 4. You can write in any manner. So this one can be written as CH2 double bond CH2. What in case of triple bond? In case of triple bond, this carbon has 1, 2, 3 bond. This carbon also has 1, 2, 3. This is shared by each of this carbon. Now this both of this carbon need only 1 hydrogen or 1 bond to fulfill tetravalency. Now 1, 1. So in this manner they are going to fulfill their tetravalency. Now this is going to be with you until you study organic chemistry. This is very important. The first and the most foremost basic thing which you need to know when you are going to study organic chemistry. Now we will begin with our chapter, that is haloalkanes and haloarenes, with the introduction. Let us begin with the introduction of haloalkanes and haloarenes. First we will see haloalkane, later we will come to haloarenes. Haloalkane, it is basically obtained by removing or replacing one or more hydrogen from alkane and adding halogen. Now, alkane has a general formula CnH2n plus 2. Alkane means single bond. So this is a general formula, and in this alkane there is removal of one hydrogen and addition of halogen. You can see here haloalkane general formula CnH2n plus 1. Here it was 2. That means one hydrogen has been removed and halogen has been added in place of that one hydrogen. Now you can see here alkane. Removal of one hydrogen from alkane and addition of halogen gives you haloalkane. Halogen means fluorine, chlorine, bromine, iodine. These are the halogens. Now let us see the classification of haloalkanes. The first one, that is monohaloalkane. Mono means one, halo means halogen, and alkane. That means this monohaloalkane is going to consist of only one halogen. Monohaloalkane is also known as your alkyl halide. Now here, this will be sp3 hybridized. I will explain how it is sp3 hybridized. The first one, RCH2X. Now here, R can be any alkyl group. Alkyl means CH3, C2H5, C3H7, and so on. The first one, RCH2X. X can be anything, fluorine, chlorine, bromine, or iodine. In this case, RCH2X, this is known as your primary monohaloalkane. Naming we will see later. Now we will go through the general view. This is primary because the halogen is attached to one single carbon, and this carbon which is attached to a halogen is further connected to only one alkyl group. Alkyl group means it will consist of carbon. That means we can say that the carbon which is attached to a halogen is further attached to only one carbon. That is why it is 1 degree. The second one, CHX. We are talking about monohaloalkane. That means it will consist of only one halogen. Now this is second degree. Second degree because the carbon which is attached to a halogen is further attached to 2 carbon. Single carbon 1 degree, attached to 2 carbon 2 degree or secondary. The third one, the carbon which is attached to halogen is further connected to 3 carbons. Remember that R means alkyl, alkyl means we are talking about carbon compounds. This carbon is further attached to 3 carbon, that is why it is 3 degree or tertiary. Now this is sp3. This is sp3 because this carbon is attached to a halogen, and the carbon which is attached to a halogen is connected with a single bond with the other carbon. Connected with a single bond, that means this carbon is going to be sp3 hybridized. Remember that single bond means it will be sp3 hybridized. We will not go in details with hybridization. Just remember that the carbon which is attached to a halogen, if it is connected with a single bond, it will be sp3 hybridized, irrespective of number of carbon atoms attached. If it is single bond, this particular carbon is going to be sp3 hybridized. Let us go to the second category, which is dihaloalkane. Di means two. That means it is going to consist of two halogens. Now this dihaloalkane is further divided into two categories, which are geminal and vicinal. Geminal means that the two halogens will be present on a single carbon. When two halogens are present on a single carbon, it comes under the category geminal. And when halogens are present on the neighboring carbon atoms, the two halogens present on the two neighboring carbon atoms, it comes under vicinal category. Let us see the third form, trihaloalkane, which means that trihalo, three halogens will be present, and there will be name in this form, halo form. You can see here, three halogens are present. When three halogens are present, it will be trihaloalkane, and when four halogens are present, it will be tetrahaloalkane in this form, carbon tetrachloride. This halogen can be anything, fluorine, chlorine, bromine, or iodine. Let us see haloarenes. Haloarenes, also known as aryl halide. Aryl means your benzene ring. So wherever you see benzene ring, you know that it will be aryl halide. Aryl halide means the halide, that is the halogen, will be directly attached to the benzene ring. If there is only one halogen, it will be monohaloarene, two halogen dihaloarene, three halogen trihaloarene. And don't get confused, instead of alternate double bond, we can also write in this form. Let us see the types of halide. The first one, alkyl halide. In case of alkyl halide, there will be only single bond, and the carbon attached to the halogen where single bond are present, this carbon will be sp3 hybridized. The second one, allylic halide. In case of allylic halide, if halogen is present attached next to double bond, it will be allylic. Here you see a double bond and the halogen is attached next to the carbon which is present next to the double bond. So in this case, this carbon will be known as your allylic carbon, and this will be sp3 hybridized because there is only single bond, and the carbon attached with a double bond will always be sp2 hybridized. Same in case of haloarenes. The halogen is attached to the carbon which is present next to a double bond. So in this case, this carbon will be known as your allylic carbon, and here this will also be sp3 hybridized because there is only single bond. Vinylic halide. In this case, the halogen will be attached directly to the carbon just present with the double bond, and the carbon attached with the double bond will always be sp2 hybridized. Same in this case also. Here the carbon, it is attached directly with a double bond. So this carbon will be sp2 hybridized, and here the halogen attached to the carbon which is attached directly with a double bond, this is known as your vinylic carbon. Now benzylic. In this case, the halogen will be attached to benzene ring. That means the halogen will be present on the carbon which is attached to a benzene ring, And in this case, since there is only single bond, it will be sp3 hybridized. In case of double bond, the carbon is sp2 hybridized. In case of single bond, the carbon will be sp3 hybridized. Before we proceed to the preparation, let us be familiarized with two types of rule, which are Markovnikovs Rule and anti-Markovnikovs Rule. These two rules will govern our entire reactions. Markovnikovs Rule says that it is applicable only for alkenes, that is, double bond. We know that single bond consists of sigma and double bond consists of 1 pi and 1 sigma. And we know that sigma bond it is stronger as compared to pi bond. That is the reason why bond breakage takes place only from a double bond. That is, pi bond will break. The sigma bond will never break because it is a very strong bond. That is why it is applicable for alkene, because bond breakage needs to take place in any reaction. So bond breakage will take place only from a double bond. We are not talking about a triple bond. Here we are talking only about a double bond. Now this rule is applicable only for Hi, HBr, HCl, not for HF. You will never see HF in any of the reactions. Now, this rule say that the negative part of the molecule to be attached across a carbon double bond gets attached to the carbon containing less number of hydrogen atom. Now, when we are taking this Hi, HBr, HCl, this is going to dissociate in H plus and their comparatively negative ions. These negative ions will go and attach to the carbon which consists of the least number of hydrogen atom, which will be clear when we see the reaction. We have this reaction. Now let us see how Markovnikovs rule will be applied here. In order to invite hydrogen ion, the electron from the double bond will shift to the carbon. Now here, this electron can also shift here. But when this electron shifts here, we will get a minor product. That means when it shifts here, the inductive effect tends to be very less. As a result, it is unstable. So the jumping of electron from this to this carbon is not preferable. Jumping from here to this carbon is much more preferable because it will give a stable product. Now, when it jumps here, as a result, this will acquire a positive charge, and since the electron is going here, it will acquire a negative charge. And in this case, chlorine is known to be an electronegative element, HCl. Why it is electronegative element? Because it has a tendency to attract shear pair of electron towards itself. Now the shear pair of electron gets tilted towards chlorine. It does not get transferred, but it gets tilted towards chlorine. As a result, it acquires a slight negative charge and it acquires a slight positive charge. Now we have CH3 with a positive charge and CH2 with a negative charge, plus hydrogen with a slight positive charge, chlorine with a slight negative charge because it is getting tilted. Even if you don't make this bond, it's fine. Now here, according to Markovnikovs rule, the negative portion will get attracted towards the carbon having least number of hydrogen. So here, the least number of hydrogen belongs to this. So this one will get attracted towards here, and the positive portion will get attracted towards the maximum one. You can see here the negative is getting attracted towards the positive, positive getting attracted towards the negative. Now this is what your Markovnikovs rule states. Negative will get attracted towards the carbon having the least hydrogen. Hydrogen will get attracted, that means the positive will get attracted towards the carbon having maximum hydrogen. we will not consider this because it does not have a charge. We are considering only this, and Markovnikovs rule applies only for double bond. Double bond breakage took place here. It is single bond, it will not be applied here. Now upon doing this, we get our product, that is CH3CH. Since the chlorine went and attacked here, we get here Cl, and since the hydrogen went and attacked here, we get a stable product, that means CH3. There will be no charge because the tetravalency of carbon has been satisfied. Now this is why I explained tetravalency, because we will get tetravalency everywhere. We have to satisfy tetravalency in every reaction. Now this is our product, 2-chloropropane. Propane because we have 3 carbons. Now remember one thing, whenever we apply Markovnikovs rule, we will always get 2 halo product. This reaction is also known as electrophilic addition reaction. Let us go to the next rule, which is anti-Markovnikovs rule. It may be V or F, it's the same thing. So this rule is also known as peroxide effect or Karash rule or radical addition reaction. In this case, electrophilic addition reaction do not take place. Only free radical addition reaction will take place. But I will not be discussing about the radical process because it will become complicated. I will be explaining in a simple manner. So this rule can be applied to alkene or alkyne. Even Markovnikovs rule are applicable for unsaturated hydrocarbons. Now this rule proceed only in the presence of peroxide. If peroxide is not present in the reaction, anti-Markovnikovs rule will not be applied. Now this very rule is not observed with HCl, HF, HI as in case of Markovnikovs rule. It is observed only when HBr is present and the reaction proceeds in presence of peroxide. Anti-Markovnikovs rule is just the opposite of Markovnikovs rule. In this rule, the negative part of the molecule to be added across a carbon double bond will get attached to the carbon containing maximum number of hydrogen. In case of Markovnikovs rule, the negative part was getting attached to the carbon containing the minimum number of hydrogen, but in this case it is the opposite. Let us see the example. We have propene, and as I have mentioned that anti-Markovnikovs rule will proceed only in the presence of HBr and peroxide should be present. Now here we have propene, we have HBr. You can see that this will break up into positive and negative part, and the negative part will go and attach to the carbon having the maximum number of hydrogen. The mechanism follows in this way. In order to invite the positive and the negative part, this bond breakage will take place. The real mechanism involves radical formation. It is not in this manner. But radical formation is not very important as of now. You just have to know how your negative and positive is going to attach. Now this will break up and it will form positive and negative ions. Now this positive one will go and attack where there is least number of hydrogen, and the positive part will go and attach where there is maximum number of hydrogen in the given compound. Now here, upon bond breakage, it requires a positive charge and it requires a negative charge. Here, the positive charge will go and attach to the carbon having the minimum number of hydrogen, and the negative part will go and attach to the carbon having the maximum number of hydrogen. Remember one thing, in anti-Markovnikovs rule you will get one halo product, and in Markovnikovs rule you will get two halo product. In this case, one numbering will be done in this manner, 1, 2, 3, and you will get your 1 bromo, 1, 2, 3 carbons, so it becomes propane, A and E, because it is single bond. You can see these rough examples in order to understand better. we have unsaturated hydrocarbon propene. Now, as per Markovnikovs Rule, the two major part is that HBr should be present along with peroxide. If HBr is present without peroxide, it will follow Markovnikovs Rule. Now you can see here HCl, CCl4. This here no peroxide, so it will follow Markovnikovs Rule, giving 2 halo product. HCl with peroxide. Now Markovnikovs Rule or anti-Markovnikovs Rule here is applied only when HBr is present along with peroxide. If some other halogen is present with peroxide, it will still follow Markovnikovs Rule. You can see here HCl peroxide. It will follow Markovnikovs Rule. If here HBr was present with peroxide, it will follow anti-Markovnikovs Rule. Since here HCl is present, it will still follow Markovnikovs Rule. Here it will give you 2 halo product. HI with CCl4, Markovnikovs Rule. HI with peroxide, still Markovnikovs Rule. HBr without peroxide, CCl4 is present, so it will still follow Markovnikovs Rule. The only case when anti-Markovnikovs Rule will be followed when HBr is present with peroxide. HBr along with any other will still follow Markovnikovs Rule, or peroxide with any other will follow Markovnikovs Rule. It will follow anti-Markovnikovs Rule only when HBr is present with peroxide. So it will give you 1 halo product. Markovnikovs Rule will be followed here entirely. This is also known as electrophilic addition reaction. And anti-Markovnikovs Rule will be followed only when HBr is present with peroxide, and it is also known as radical addition reaction. Let us see how naming is done for haloalkane. Common name. The common name will follow in this manner. Alkyl halide. Alkyl will be the carbon chain, and your IUPAC name will be haloalkane. In this manner, alkyl halide. Alkyl, if we have methane, if we have just 1 carbon, it will be methyl, and halide, if we have chlorine, it will be chloride. In this manner, here we have 2 carbon, so it is ethane. So according to this alkyl, it should have YL as the ending, so it will be ethyl, and since we have chlorine, according to this the ending should be IDE, so it will be chloride. So the common name for this will be ethyl chloride, but when we go to the IUPAC name, it should be haloalkane. Halo, if we have chlorine, it will become chloro, ending will be O, and alkane will remain as it is. Here we have 2 carbon, so our ending will be ethane. Our first word for chlorine, it will become halo, that means it will be chloroethane. This is how we are going to follow the naming. I'm sure all of you know for 1 carbon it is met, 2 eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, and so on. This is the common thing, so I will not be going in very much detail. Now let us see how naming is done. The first thing you have to do is numbering. How will you do the numbering? You have to keep in mind that your substituent, mostly in this case will be the halogen, should be given the least number as possible. Now here our substituent, we have 2 chlorine. So we have to keep in mind that when we are numbering them, we have to give them the least number possible. If we give the number from here 1, 2, 3, 4, 5, then it gets the number 4. Chlorine gets the number 4. But if we number from here 1, 2, 3, 4, 5, it gets the number 2. So this will be our preference. And remember that numbering will be done only on the carbon atom, not on any other atom. So here our numbering will be done in this manner: 1, 2, 3, 4, 5. Now if more than 1 halogen is present, we will use the prefix di, tri, tetra, and so on. In this case, your IUPAC name, we will do for the IUPAC name halogen will be named first. In this case, since we have 2 halogen, first we will write, since this 2 halogen is connected to the carbon having number 2, it will be 2,2-dichloro. Since we have 2 chlorine and chlorine, halogen will be named as halo. Now our next thing will be to name the other substituent, which will be our methyl. Now methyl is in number 3, so it will be 3-methyl. Now we will name the carbon chain. How many carbon are present? 1, 2, 3, 4, 5. So 5 carbon, it will be pentane. The second one, first we will do the numbering and we will make sure that the halogen get the least number. So we will number from here 1, 2, 3, 4. Now our second way of doing is we have to search for the longest carbon chain. Now if we proceed in this manner, we just have 4 carbon. But what if we break this and write in this manner? CH3, C, C, C. This can be broken down into CH2 further CH3. This should be C2H5. So if we break this C2, we are getting 2CH5, we are getting 5. Now from here we are getting only 4 carbon. But if we proceed in this manner, 1, 2, 3, 4, 5, we are getting 5 carbons. So our next criteria is that we have to look for the longest carbon chain. So our preferred compound will be this. It is the same compound, but we are breaking this and we are getting a longer carbon chain, so we will prefer naming this. Now here, since 2 halogens are present, first halogens are named, but when 2 different halogens are present, what we will do is we will name in alphabetical order. Bromo, chloro. First B comes, then C. So first bromo will be named, followed by chloro, then followed by the other substituent present. Now here, this is our carbon chain. So which will be our next substituent? This will be our next substituent. The carbon where we do not put the number becomes our substituent. So here we will name in this manner 2-bromo, 2-chloro, because both the halogens are present in the same carbon, but they are different halogens. That is why we will not write it together but separately. 2-bromo, 2-chloro. Our next substituent is 1, 2, 3. This one, methyl. Methyl is attached to the third carbon, so it becomes 3-methyl. Then we have no longer substituent, so we will name the carbon chain 5 carbon. That means it will be pentane. So the name will be in this manner. Coming to this. Now here, first we have to count the carbon chain. 1, 2, 3, 4, 5. Now even if we break these, we will get 1, 2, 3, 4, 5. So in this case, in both the cases, we are getting only 5 carbon chains. So there is no point of breaking. Even if you break, you will get pentane. Even if you don't break, you will get pentane. So we will prefer not breaking it, because in the 2 cases also we get the same thing. So here we will name them 1, 2, 3, 4, 5. Here the same thing follows. 2-bromo, 2-chloro. Our next substituent is this group. Now this group, since we are not breaking it, C2H5 is ethyl. So here it becomes 3-ethyl, carbon chain 5, so it becomes propane. So in this manner, you are going to name your given compounds. The first compound given in your notes, here halogen should be present, kindly correct it. Now here, if we number from here 1, 2, 3, 4, 5, halogen get the number 4. But if we number from here 1, 2, 3, 4, 5, it gets the number 2. So the least number will be preferred for our substituent. Now, how many carbons are present? 1, 2, 3, 4, 5. So it becomes pentane. Now let us write the name. chloro. Now let us see how many substituents we have apart from chloro. 1 and 2. So this is a methyl group. So methyl group, the both methyl group are present on the 2 and 3rd carbon. So it will be written in this manner: 2,3 dimethyl. Why dimethyl? Because 2 methyls are present. Then the carbon chain, 5 carbon chain, so it becomes pentane. Now let us see how can we name such branched compounds. Here, whenever we have this, if there is nothing present at the edges, know that CH3 is present. And here, these are all carbon chain. Now this, how do we break down in a hydrocarbon chain? Here, as I said, CH3 is present. So, it will be written CH3. Here, again C. Remember, we have carbon everywhere. Now, I have explained about tetravalency. Why I have explained? Because here, in every compound, tetravalency needs to be fulfilled. If you are still confused with tetravalency, watch the first video. Now here we already have 2 carbon, 2 hydrogens. We need tetravalency, so here it will become CH2. Here already 1, 2, 3 hydrogens are present, so it will be CH. Here nothing is present, so assume CH3 is present. Now here again 1, 2 hydrogens are present, so it will be CH2. Here already double bond is there, so for this carbon how many hydrogens are there? 1, 2, 3, so only 1 hydrogen will be placed. Double bond. Now for this, how many hydrogens are already there? 2 hydrogens. How many it needs to fulfill tetravalency? 2 more, so it will be CH2. So all together we have 1, 2, 3, 4, 5, 6 carbons. Now we have to name this. Now this is an alkene. Now here there are no halogen present. So our first motif will be double bond should get the least number followed by the substituent. So here double bond is here, so numbering will start from this place. 1, 2, 3, 4, 5, 6. But while we are naming them, the substituent will be named first. Remember, the alkene, the double bond will be given the least number, but the naming will start from the substituent. So here methyl is numbered as 4, so it will be 4 methyl. Now we do not have any more substituent, we will directly go for naming the carbon chain. Now in this case where alkene is present or in a branched form, when you write down the name of the carbon, it will be written only in this manner: HEX, hex, followed by naming the alkene group, that is number is given 1 and it will be named as ENE. Or this one can also be written 4 methyl 1 hexene. You can follow any process. Now for the 6th one, here as I said, when nothing is mentioned, it is CH3, but remember it is a double bond. If you put here CH3, the tetravalency will be destroyed. 3, 4, 5, it will be 5. It should have 4 hydrogens only. So here what we will place? CH2, double bond. Here C, count the number of hydrogen, 1, 2, 3. So we will place only 1 hydrogen. Then carbon here, 1, 2. So it will be CH2. Here directly CH3. So 1, 2, 3, 4, it is a propene. So here there are no substituent. So 1, 2, 3, 4, you can name this as PROP1-ene because your double bond is at first position, or directly as propene. For the 7th one, kindly draw the double bond if it is not given in your notes. Here let us write the carbon chain first. Here it will be CH3. Remember, everywhere we have C. Then we have to fulfill their tetravalency. Here CH3, single bond, 1, 2 already. So CH2, 1, 2, 3. So it will be just CH. 1, 2, it will be CH2, CH3. Single bond, 1. Now for this carbon. 1, 2, 3. Already 3. So just 1. Double bond, C. How many? 1, 2, 3. So H only. Now here it will be CH3. Now followed by, here it will be again CH3. Now let us try to name this compound. Now here, let us see the longest carbon chain. 1, 2, 3, 4, 5, 6. This can be one carbon chain. Now let us see how many carbons are present in straight way. 1, 2, 3, 4, 5, 6. Same. It is 6, 6 in both cases. So we need not go in this manner. We can go in this manner. There is no problem. You will get the same name. Now here, let us do the numbering. This one should be given the least number. So it will be 1, 2, 3, 4, 5, 6. So the naming will start firstly from the substituent. Now here, in the fourth position, we have our substituent. Now, since we have two carbons here, we will take as a whole. This is the ethyl group. So it will be 4-ethyl followed by naming the, we have our second substituent here. This is the methyl group. So it will be 2-methyl. Now, why did we not name methyl first? Because as I said, in the halogen, when two halogens are present, we will name them in their alphabetical manner. In the same way, since here two alkyl groups are present, we will name them in their alphabetical manner as well. M comes second, E comes first. So we will first name the ethyl followed by the M. Now we will name the double bond. Now 1, 2. The double bond is present with the 2. Now it is not present with the, it is present with the third carbon also, but we will consider, when we are writing, we will consider for the first carbon. So it will be 2 in. Before we name the double bond, we have to name here the number of carbon chain. So it is 6. So it will be hex. Or this one can be written as 4-ethyl, 2-methyl, 2-hexene. It can be written in this manner as well. Now going to this number 8, we will break it in the chain. That is here C, 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 C. Now how many C? 1, 2, 3, 4, 5, 6, 7. So first one is CH3. Second one, 1, 2 carbon already, hydrogen already. So it will be CH2. For this one, we have 1, 2, 3 hydrogen. So it will be CH followed by this carbon already 1, 2, 3. So it will be again CH followed by this one already has 1, 2, 3. So it will be again CH followed by 1, 2. So it will be CH2 then CH3. 1, 2, 3, 4, 5, 6, 7. And your halogen is present here. Your double bond is present here. Now let us see the numbering. Here 1, 2, 3, 4, 5. 1, 2, 3. When double bond is present, our priority is our double bond. That double bond should get the least number followed by the substituent. So we will proceed in this manner. 1, 2, 3, 4, 5, 6, 7. So while writing down, we will write down the substituent first. So 5-chloro. Then we do not have any substituent, so we will go for naming the carbon chain. So it is 7. So it becomes hept. Where is the double bond? Third position. So it will be 3-ene. Or simply 5-chloro, 3-heptene. Now, this naming of the carbon chain or nomenclature will become familiar only when you keep on practicing. Let us see how can we name monosubstituted benzene. In case of monosubstituted benzene, the common name and IUPAC name is the same. Here, first you will name the halogen followed by the benzene. Here, we need not put any number, directly the name will be, since it is benzene and it is chlorine, we always refer the halogen as halo, so the name will be chlorobenzene. But in case of dihalosubstituted compound, where two halogens are present, the common name, the prefixes like ortho, para, meta will be used in order to indicate a position of the second halogen atom, not the first one. And your IUPAC name, your position will be decided with the numbers. Now here, the position next to the halogen or the alkyl group is known as ortho position. This is known as meta position and this is known as your para position. Now how do we name this compound as per the common name? So here we have ortho, this is meta. So this becomes your meta. How many halogens are present? 2. So it becomes dichlorobenzene. This is your common name. Now when we are to write the IUPAC name, it will follow with a number 1, 2, 3. Your numbering will start from the first halogen carbon first. Here carbon attached to the halogen will be 1, 2, 3. Now we can go in this manner also 1, 2, 3, 4, 5. So if we go in this manner, we get the numbering for the halogen is 1, 5. But if we go from here, we get 1, 3. So we will prefer the number which is least. We will never go for the number which is maximum. We will only prefer the least number. So your IUPAC name will be 1, 3, dichlorobenzene. Dichloro, same in case of common as well as IUPAC. Only the difference is in their position. The first common position you will indicate as ortho, meta, para, and your IUPAC position you will mention as the numbering. Now if we have this chlorine present in different position in this manner. Now here this is the ortho position. So your common name will be ortho dichlorobenzene. And your IUPAC name will be 1, 2, dichlorobenzene. Now this is how you are going to prepare your nomenclature. Keep on practicing, it will become very easy.